see. All right, so announcements before we start. On Sunday, you have that Chapter 7 homework quiz that's due. It's part 2. So it's all about like naming compounds, knowing the charges or the oxidation numbers, which we're going to talk about today, and then also referring to the octet rule. So know how to name compounds, know how to come up with chemical formulas for that quiz. On Wednesday, so this is a reminder, we've already talked about this in detail, InfoLit paper's due. So it's due on a Wednesday, not a Sunday, so I just want to remind everyone of that, get working on it this weekend so you can get that in. It's worth the same amount as a test score. So it's a lot, 10%. So, and it's only 2.5 pages, maybe 3. So it's your chance to make up for any tests you might have done poorly on. You can really up your score with that. All right, so we're going to continue on with naming. So we talked about covalent naming, where we use prefixes and IDE endings. We started naming ionic compounds, but just the main group metals. So I'm going to refer back to the periodic table a little bit to talk about ionic compounds a little bit more and how we get the charges. Because when we get the name of an ionic compound and we have to come up with the chemical formula, we need to know the charges of the elements in that compound in order to figure out what the formula is. So I want to talk about where these numbers come from. So the periodic table we talked about last time is split by this zigzag line, and you can see on your periodic table it's just a bold line that's zigzagging down, starting at boron and going between boron and aluminum. This line is separating the nonmetals over here from the metals, which is all this side. And remember, the exception is hydrogen here. This is not a metal. This belongs over with the nonmetals. Anything touching the zigzag line, with the exception of aluminum, are metalloids. So this helps us identify the type of compound, because covalent are nonmetals, or metalloids, and ionic are a metal with a nonmetal. Okay, so we need to know the type for when we start naming it. Now, the charges that I have up here, these oxidation numbers, those are only used in ionic compounds. So that's why we're talking about them in more detail now, is because we're looking at ionic compounds. So for the main group metals, we know what the charge would be when these elements are in an ionic compound based off where they are on the periodic table. So the alkali metals, this group 1 here, always +1. Alkaline earth, always a +2. This +3 is referring to aluminum because that's the only metal. And remember, metals form cations, they form positive charges. And then when we get to the nonmetals, we see negative charges. -3, -2, -1. But why do we get these charges? Why are they +1, +2, etc.? This is due to the octet rule. So what the octet rule is it's saying that everybody wants to be a noble gas. They want 8 electrons, that makes them stable. When we say they want 8 electrons, those 8 electrons we're talking about are in their valence shell. So here's the structure of an atom. We've got the nucleus in the middle where the protons and neutrons are, and then we have energy levels or rings on which the electrons are orbiting that positive center. So the valence electrons, it's the outer shell only. So it would be this outer shell furthest away from the nucleus. So the octet rule is saying that all of the main group, just the main group ones, so here and here, not the transition metals, all the main group ones want 8 electrons in their valence shell. That's what makes them the most stable. So if they have 8, now they're happy, everything is good. So the reason for these charges is because these elements get these charges to fulfill the octet rule. For instance, let's look on the bottom here in green. These are the number of valence electrons that these elements already have, without bonding. Right? So the alkali metals always have 1 valence electron. That's just how many they naturally have in their natural state. Alkaline earth have 2. So it's kind of easy to remember these because you just skip the transition metals and just count. 1, 2, 3, 4, 5, 6, 7, 8. Now notice this 8, that's already filling the octet rule. So that's why this group, the noble gases, don't have a charge. Because they already have 8. They don't want to gain electrons. They don't want to lose electrons. They're happy. It's everybody else's goal to get 8, like the noble gases have, so that they can be happy too. And how they get 8 is by gaining or losing electrons. So, for instance, let's start with the halogens here. So the halogens, all of them, fluorine, chlorine, bromine, iodine, etc., they have 7 valence electrons. The octet rule says they want 8. So to get 8, what they do is they gain 1 electron. Well, if they gain 1 electron, electrons are negatively charged. So that's why they form a -1 charge, because of that extra electron they gain so that they can get 8. For oxygen, sulfur, selenium, they're a -2 charge because they're 1, 2 away from becoming a noble gas. So they gain 2 electrons to get a -2 charge. Nitrogen, phosphorus, arsenic, same thing. They're 3 away, so they gain 3. So the negative charges kind of make a little bit more sense than the positive. Let's look at the positive though. It might help to draw a structure of it. So I'm going to draw an atom of, let's do beryllium. It's going to form a +2 charge. So how many electrons does beryllium have? 4. So it's going to have 2 here, and it's going to have 2 here. I think that was the best example. Let's not do beryllium. We'll do magnesium instead, because magnesium has 12 electrons. So this would be an example of magnesium. Magnesium ion. So what happens here is magnesium has 2 valence electrons. So that's what this outer shell is showing. Okay, this is that valence shell with 2 green dots representing the electrons. So magnesium has 2 choices to fill its octet. One choice, it can gain 1, 2, 3, 4, 5, 6 electrons to become a -6, or it can simply lose those 2. So all the elements, they go through the path of least resistance. And it's easier to lose 2 than it is to gain 6. So that's why the metals always lose, the non-metals always gain, because they're just closer. So when it loses its 2, it's going to lose these 2 electrons. What happens is this is no longer its valence shell. Now the next shell down is its valence shell, and the next shell down has 8. So that's how it forms or commits to the octet rule. So the metals always lose to fulfill, the non-metals always gain to fulfill. So that's why the charges. All right, so let's look now at naming. So we already looked at naming the main group metal ionic compounds. So the first type, I call them binary. And this is where we just took the metal name and then the non-metal with an IDE ending. Okay, so this is the simplest form. An example would be Li2O. So the metal always comes first in the chemical formula. Li is just lithium, so you just write lithium. Doesn't matter that there's 2 because we only use prefixes for covalent. And then the non-metal, oxygen, here is oxide. Okay, so these are the simplest ones to name. So we're going to take it a step further, and I handed out a sheet. There's also one posted on Blackboard with some polyatomic ions on it. So we're going to look at naming ionic compounds that consist of polyatomics. And what a polyatomic is it's covalently bound ions. So the ions themselves are bound covalently, so they're sharing electrons, but they have a charge. So since they have a charge, they're referred to as ions, and ions are present in ionic compounds, hence the name. So these polyatomic ions are only used to form ionic compounds. So naming these actually isn't that bad either. It's mainly just recognizing that there's a polyatomic in it. That's the hard part. So Let's start with an example. So if I had CaCO3. So how would you know a polyatomic's in there? Well, the key is if you have 2 or more elements present. That's what tells you it's a polyatomic. Because up here, and in all the other examples we saw, we only have 2. That's why we call them binary, because bi for 2. We had lithium, we had oxygen. Down here, we have Ca, calcium, carbon, and oxygen. So we have 3 elements present. So that tells you that one must be a polyatomic. So that's when you go to your polyatomic table and try to figure out what part of it is the polyatomic. And this will become more natural once you name more of these. But most often, it's the anion, the anion, the second half, the negatively charged portion, that is the polyatomic. Because if you look at your polyatomic table, and there's way more than this, we're just going to look at the common ones in this course, but if you look at it, almost all of them are negatively charged. So almost all of them are anions, which means they're going to make up the second half of that chemical formula. The only cation, the only positive ion that we have in the polyatomic table is that NH4+, the ammonium ion. So if you know there's a polyatomic, almost always it's going to be the second part of that that is the polyatomic. So to name it, we're actually naming it very similarly that we did with the binary. We're going to name the metal first. Ca, in this case it's calcium. And then the non-metal portion, since it's a polyatomic, we're not going to add an IDE ending. So that's the difference with the polyatomic. No alternate endings. You're just going to find this on the table and name it exactly how it's written on the table. So CO3 is carbonate. So you just write carbonate. So I'm going to try one more, and then we're going to do where we take the names and come up with the formula, because that's usually the harder direction to go when it comes to ionic compounds. So just trying one more, we have, what is that, beryllium? Yep. So I wanted to show this one, because here's another clue that you have a polyatomic, is if you have parentheses. Anytime you see parentheses, there's a polyatomic somewhere in there. And it's usually, the polyatomic is usually inside the parentheses. All right, so in this case, we're going to do the same thing. It doesn't matter that there's 2 of these polyatomics because we're not using prefixes. Okay, so it doesn't matter in the naming of it. So we look up Be on the periodic table. It is an alkaline earth metal in group 2. It's beryllium, and I'm going to spell it wrong. Something like that. And then NO3 you would look up on your table and write it just how it's written on your table. In this case, I believe it's nitrate with ATP.
So then if you have to, like say if someone just read it, they'd have to know how many of the polyatomic areas they'd have to do the charges.
They'd have to do the charges, exactly. And that's what we're going to do right now. We'll do an example or two before we do the transition metals, which is the hardest one in my opinion. So I'm going to put a name down, and we'll come up with.
So do chemists just have all those just memorized?
Yes. Yeah, you just use them day to day. Maybe not the formulas themselves. You might have to do the charges yourself. Because I don't have the formulas memorized. If I see the name, I can't just come up with it right away. Sometimes I have to go, okay, what charge? And then we do it mentally. But let's look at acetate. Okay. So a couple things you can tell just by looking at this name. First off, no prefixes, so it's not covalent. You can tell that right away. If you weren't sure, the fact that it has aluminum, which is a metal in it, tells you it's also ionic. Now, for the acetate portion, notice the ending, ATE. That ending tells you there's a polyatomic, because If it's an element off the periodic table, we have an IDE ending. Okay, so that's your clue that you're going to look in the polyatomics. So what we do now is we find aluminum with its charge, we find the acetate ion with its charge, and then do that crisscross. So aluminum, based off where it is on the periodic table, that's how we figure out its charge. It has 3 valence electrons. It's going to lose all 3 of those to get a full octet to become a +3. What about acetate? I don't know that chemical formula offhand. C2H3O2? I already forgot it.
C2H3O2.
Thank you. -1 charge? So now, we notice the charges don't cancel. So if they don't cancel, that means we need more than one of something. So that's when we do that crisscross. So this 3, not the charge, just 3, becomes a subscript on the polyatomic. This 1 will become a subscript on aluminum. So we're saying we want 1 aluminum, and I don't need to write the 1 because that's assumed. But now for the polyatomic, the key here is I don't want to just put the 3 here and leave it at that. This is wrong. Because what this tells me is I have 23 oxygens and 3 hydrogens and 2 carbons. That's not what I want. I want 3 of the entire polyatomic. So that's why the parentheses. So if you have more than one of a polyatomic, make sure you put parentheses and then the number on the outside. I will give you both options in a multiple choice. So make sure you're picking parentheses if they are needed.
You said we have to do the crisscross because it didn't cancel out.
Right.
What is it?
So for instance, the charges, so if I had 1 aluminum and 1 C2H3O2, if I add those together, a +3 plus a -1 gives me a +2. And I need it to equal 0. So for it to equal 0, if I had 3 of these, +3 plus, that would be -3, then it would equal 0. So the crisscross method just kind of figures out for you how many you need of that other one. There is the longer way where you can just like add them, I think that I showed in the last video. So we'll do more examples with polyatomics, but I want to bring in the transition metals because more practice we can have with those, the better. So the transition metals are difficult because so far, all of the ions that we've used, we can figure out the charge simply by looking at either the periodic table or the polyatomic table. Transition metals, no. They're all over the board. So transition metals can have what we call variable charges. And what variable charges means is that they can have more than one charge. Okay, so copper, for instance, is a transition metal. Copper can have a +1 charge or a +2 charge. Palladium can have a +2 or a +4. I mean, it just depends what element, and there's no way of knowing that unless you looked it up. You can't tell just by looking at the periodic table. This would be something you either would have to memorize or look up. But at the same time, for instance, copper I said could be a +1 or a +2. Looking at a chemical formula, there's no way of knowing which one unless you do what I call the reverse crisscross. So we're going to figure out the charge based off of the formula. Okay, so before we do that, we're going to use a formula to come up with a name. So to name these guys, we're going to do the metal first, but the metal is going to have a Roman numeral after it. So that's the difference here. A Roman numeral after the metal name. And that Roman numeral is going to represent the charge, or the oxidation number. So if I'm talking about the copper +1 ion, I'm going to put a Roman numeral 1. Copper 2, Roman numeral 2. Okay? The non-metal portion is remaining the same. If it's a non-metal, we're going to add an IDE ending. If it's a polyatomic, we're gonna write it straight off the polyatomic table. Okay, so that part's not changing, it's only adding this Roman numeral. So an example, I'm coming prepared because I don't think of one. Let's do, we're naming it, right? So I need the chemical formula. So we do cobalt. COS. And this is a little o, so it's not oxygen. That's how you can tell if it's one element or more than one. So capital followed by a lowercase, that's all one element. So COS, kind of a weird one. So when you look at this, in order to name it, you have to figure out the type. You'd find cobalt in the transition metals. It's actually number 27. So it's a metal, and then S is just sulfur. So it's a nonmetal. So metal, nonmetal, ionic. So we know we're going to be naming it this way. Furthermore, since cobalt's a transition metal, we're going to have to include a Roman numeral. So when we do the Roman numeral, it represents the charge. So we have to figure out the charge on cobalt before we do anything else. I said I don't know the charge, right? It can be multiple. So that's my question mark. So how do you figure out its charge? You look at what it's attached to. That's what's gonna help. So sulfur, I can figure out the charge on sulfur because it's right here, under oxygen. Everybody in this group has a -2 charge in an ionic compound. So -2. And just like we did before, trying to get the compound to be neutral, we're gonna do the same thing here. So if I have a -2 here and there's just one atom, what's my charge have to be on cobalt to cancel out that -2 charge? A +2, exactly. So using the known, we can figure out the unknown. So now that I know the charge, I can name it. And I'm just gonna write cobalt with metal name, no prefixes, nothing fancy, but I will put a Roman numeral 2 after it because it's cobalt 2, not cobalt 1 or cobalt 5 or anything like that. Now sulfur, that's the nonmetal portion, so I'm going to change that and add an IDE ending to become sulfide. Let's try it for now. That's not what I wanted. I wanted D, not PD. All right, so the fact that there's parentheses probably tells me it's ionic because that's got to be a polyatomic. That's what the parentheses usually mean. And it's a metal with a polyatomic in this case. Now when I look up PD, I notice it's not a main group metal. It's number 46. It's a transition metal, so I'm going to need a Roman numeral indicating its charge. So I need to figure that out first. To figure out the charge, we look at what it's attached to. Because this one we can look up since it's a polyatomic and we have polyatomic tables. And what is that, permanganate? Yes, permanganate, and it's got a negative. So it just says negative on your polyatomic, that means it's just a -1. But you need to take into account how many there are of them. Okay, so this 4 on the outside, it's saying there are 4 permanganate ions. So since we have 4 of them, what's our total charge? -4, exactly. 4 of them, each with a -1 charge, gives me a total of -4 on the anion side. So what charge do I need on the cation side? +4. And since there's only one atom, that entire charge goes on that one palladium. So in this case, it's palladium 4. So when I write it, I'm going to write the name, metal name, no changes, and then add a Roman numeral indicating that it's the +4 ion. And then the polyatomic, just copy it off the table, your polyatomic table.
know that Tyler guy on YouTube said, or do you have to put them in parentheses from the numerals? Or is that not necessary?
You don't have to put them in parentheses. You can see it, you'll see it both ways. I used to put in parentheses all the time. So you might see that on some of my PowerPoints, but you don't need to. Does DeWitt do it? Tyler DeWitt? That's the guy.
Yeah, that's-
He does put them in parentheses. And I'm talking just the Roman numerals. I mean, the polyatomics do have to be in parentheses if there's more than one,
Yeah.
just to specify that. Okay. Let's try going, well, the other direction is pretty easy. Let's do one more, because I want to show one with, we might have to do some division, so now I got to think of one. Did you like his videos? I like his videos. How to do it?
Yeah, it makes me wonder what, I feel like a lot of chemistry teachers are too smart for their own good, so they don't know how to simplify things.
Where to start? Because
Like
yeah,
my high school teachers.
they assume it in their heads, I think a lot of teachers, and then they don't
Yeah,
go to the
'cause it's
base
so simple
level.
for them, they kind of lost how to.
Yeah, I
Yeah.
agree. That's why I like him, he really slows it down. I think what I want to do here. That's what I want. Okay. Sorry. I was trying to do the reverse in my head. This one gets funky, I think. All right, let's name it. Mn, manganese, transition metal, oxygen, non-metal, so ionic compound. Since it's transition metal, we're using Roman numerals. So we got to figure out the charge. Look at its partner, oxygen. -2. But there are 2 oxygens. So what's my total on the anion, the negative side? -4. 2 atoms, each with a -2 charge to give me a -4. Almost ended up being an easy one too. So that means we need a +4 on the cation side, correct? So since there's only one of them, that entire charge has to go on the metal itself. Okay, so just like the last one, essentially, we're writing manganese this time, and then 4 Roman numeral, oxygen becomes oxide. Let's do the reverse. I'll put some names down and we'll come up with the formulas. And you'll see those are kind of nice because they include the charge there for you. So transition metal, names. All right, so the presence of the Roman numeral tells you it's a transition metal, but you could also figure that out by finding where they are on the periodic table. So remember, this Roman numeral indicates the charge, because when we're naming ionic compounds, the first thing we want to do is find the symbols and the charges, right? So iron, the symbol for that when you look at the periodic table, is Fe for ferrous or ferric, depending which cation you have. And the charge on it, you just look at the Roman numeral, +2. Now, nitride, so it's got an IDE ending. So this tells me that it's nitrogen on the periodic table just with that alternate ending. So its charge, N, is going to be -3. Do the charges cancel? No, so we're going to crisscross them. So the chemical formula becomes iron, 3, and then nitrogen, sub 2. Fe, 3, and 2. have 3 irons, I'll have a +6. If I have 2 nitrogens, I'll have a -6, neutral. Next one, ruthenium 3. Ru, what's the charge? +3. So you know it's a 3 because of the Roman numerals. The reason we know it's a plus is because it's a metal. All metals form cations, always a plus for the metals. And then oxide, since it has an ID ending, I know it's an element from the periodic table. So just O, based off where it is, I know it's a -2. Once again, charges don't cancel, so I cross. So I get Ru 2.
Wait, so you're just taking so you don't have to do any math, you just switch the numbers?
You just switch the numbers and it
Does that
does the
work
math
all
for
the
you.
time?
Because if I have 3 oxygens, right, that means I have a -6, right? 3 times a -2. If I have 2 rutheniums with a +2 charge, 2 times a +3 is a +6. So it does it for you. If you did it the long way with the math, you're going to get the same result. This is just a shortcut to getting the correct answer.